That work?
Yeah.
Okay. Hello, everybody. Thanks for inviting me or being voluntold. For those of you who have more knowledge about this. So, first things first, as you can see, thanks for overselling it, Nixon, with expertise, and etc. If you just look at the title, I mean, that already tells you the kind of person who's going to give you a talk, right? I'm just playing with the words on edges and dots for networks. So why not? It's really an overview, right? I was told that we can have a diverse audience. So no Monte Carlo chain explanations, no formulas, I think, etc. So feel free to just, at any point, just go, hey, Baldy, can you please explain this again, whatever. I'm good with that, not a problem. And otherwise, let's just go for it. Try and make this smaller. It's not making smaller. Okay, that's better. So there I am. So the main objectives to introduce some concepts, to discuss the utility of visualization networks, present some existing methods, and exemplify some of the utility of some network applications. The outline, I'll touch on what are some types of networks, what are networks, how people have studied them for a while, some of the statistical issues with studying networks, modern social network analysis, and some examples, right? So types of networks. So yes, in everyday life, right? I mean, this talk, I think I gave some kind of talk like this, and it was named, no, it's not about Facebook, but sure, Facebook is a type of network, right? I mean, I think they don't depict that way anymore, but it used to be. So it's a network, people connecting. You can think of transportation networks, and maybe we could throw in the buses in there, and then you have more networks, more connections. You can think of trade networks, right? You could be thinking of communication networks, and you could be thinking of, electricity, power grids. These are all different types of networks, connections, right? So now more special or specific ones, more so when it comes to the social.
I can continue.
Okay, to the study of social or health issues, right? We can be thinking of, friendship, kinship, teamwork, collaboration, publication, right? Why are this important? Well, sometimes when you're looking at things I've seen things when you're doing implementation in hospitals or whatever, you really want to know. I felt like I was talking to myself. Anyway, it's you can feel you want to see how the information will flow, etc. Right? So there's several things that this may be important, right? In a nutshell, a network is any set of actors that can be tied or connected in some way by some kind of relationship. Right now, this is very broad. You can open the definition of relationship in many ways. More formally expressed, again, a web or linkage among a defined set of social entities, right? So usually we talk about actors, right? And more so now with the newer analysis that it's on stochastic actors, etc. So the actor part is emphasized, right? But you can think of anything: individuals, clubs, countries. The only constraint we usually set is that when you're analyzing a network, you can consider them to be of the same kind, of the same level, right? And when I say level, it doesn't mean, because you could be looking at the structure when they did some analysis on the Enron issue, etc. Well, you have at different levels of work, but they were all people employed by Enron, right? So you can still have hierarchies in that sense, but we're not mixing agencies with people, right? And the edges are usually your connections or the ties that establish some kind of linkage between the actors. Now, these can be formal relationships, right? They can be due to authority, or they could be induced from club membership, or again, just friendship or things you want to do, right? Now, again, the constraint is that all edges or ties within a network must represent the same type of relation, right? Now, that's some of the most basic networks. You can have networks that they call multiplex, right? So you have different relationships within the same network. Some of the work we did with the students in a room, it was the I play with, I'm friends with, I visit home, I don't get along with. So you have different relationships, but each of those relationships is in its own network. Oh, good. Now, the main separation usually is whether you have a one mode or two mode networks. One mode network, well, everybody is kind of the same thing, right? So all actors are of the same kind, right? So links between people, links between agencies, right? And then you can have the two mode networks, which involve two different set of actors. Within each set of actors, again, they're homogeneous, but you could have, events and people, right? So people that attend events. And from here, you can actually also people do affiliation networks, right? So you could convert a two-mode network to a one-mode network by saying, well, P3 and P5 are connected because they both went to E6, and then you do away with the events, and then you just look at people connected, right? Now, a little bit of where all of this came, right? So there's many authors that cite Moreno in the 60s, I think, or even before that, to start doing like more scientific study of networks. It was Moreno who formalized the idea of let's represent them, right? Let's have little dots for nodes or actors. Let's have edges or ties to look at the relationships. They were called sociograms, right? So that was where they first started, and the little dots are our nodes, and then we have our ties, right? So ties, edges. So the edge, physically, graphically, it's an edge, but it's representing a tie or a relationship. Now, at the start, they really wanted to look just at some things that had to do with behavior, right? But mainly about how was that behavior or that structure within a network. So some of the basic things started that. Then we started looking at more of how the social structure is having an impact potentially on behavior or attitudes, right? One thing could be that given the structure of a network, then you have certain behaviors, right? So you can think again of a hierarchy in a company. Well, I may not necessarily go every day to talk to the CEO, right? So my communication is set by the structure. But if you actually have the other way around, right? You could be thinking of, well, if we're really well connected, then we create a certain structure, right? So sometimes structure leads to behavior, sometimes behavior can lead to structure of a network, right? So you could bring being a smoker may lead to a greater number of friendships with other people being with other smokers, right? So you create a network of only smokers because of your behavior rather than because the other way around. Yeah, sounds good. Now, then the main idea was to start doing some visualization, right? And they established a mathematical ways it is related to graph theory for some things. So again, boils down to ties and nodes. Now, I won't be discussing like why does it look this way. There are many layouts that you can use, right? Some of the more used layouts, which is how this one was created, is it's a balance of how many ties get crossed, how many nodes get overlapped, and it has some kind of optimization behind the scenes, right? But you could actually do, and you see this a lot in many of the web pages of universities when they look at the ties between your network of collaborators. They usually use the circular one, right? So everybody's in the periphery and you have the little colored ones coming and going all around, right? So that's just another setup of doing the graphs, but you still have nodes and ties, right? So now, how do we represent this mathematically? Well, we have a matrix, a socio-matrix or an adjacency matrix, right? Because who's adjacent to who's connected to whom, right? So let's say we have this adjacency matrix. So you have rows and columns where you have the nodes on both of them. The way you use the social matrix is to read row sends to column, right? If you have a directed network, if not, well, it would be symmetric, right? So in this case, N1 sends a tie to N3, and N3 doesn't send one to N1. Yep. So who sends to whom, right? A directed network, in this case, N1 sends something information. I consider you my friend, but you don't consider me your friend. So that's a directed network, right? So this represents, in that case, that one, right? And that social matrix gives rise to this one. You could see that N11 was all alone, isolated, sad, right? Most likely me, but anyway, right? Now, who sends, who receives, right? So the directionality is important, right? Why is it important? Because again, we are looking sometimes at mainly social things, right? So advice seeking, right? It's directional. I may actually come and ask you if you're way know more about certain things, or if I believe you know more, and you may say, "No, Alberto's always, BS. I'm not going to ask him anything," right? So seeking advice can be directional. Falling in love, right? It's directional, right? Uh, so the directional networks may be asymmetric, right? And I say maybe because maybe you do send love back, maybe you don't, right? Now, reciprocity in this case also becomes important, right? So if I send, what is the likelihood that you send back, right? So it's something that becomes important when you have directionality. Now, some relationships, just by the way they are non-directional. Doesn't matter how much you push them, right? So kinship, if I'm a sibling of someone, that someone is my sibling. I mean, you can say I disown you and I don't know it, but you are still related, right? A marriage, I'm married to Luz, and hopefully she thinks she's married to me too, right? That would be the hope. Co-authorship, right? Well, we are on the same paper. Yeah, you can say who's first, second, whatever, but we are on the same paper. So there's no directionality that you can actually induce from that. Non-directional networks are symmetric, right? Because then, since we're always reading row to column, well, you have to have things coming that way. Yeah? Okie dokie. So how does a directional network look? Most of the time, we use the arrows so that you can see who's receiving the action. Non-directional networks, you don't need the arrows because as long as you're connected, it comes both ways. Yeah? Now, not all networks are just, are you connected or not, right? There is importance in what else is happening, right? So apart from existence of connection, you could think of what is the strength of the connection, right? Whether it's information that's flowing, how much I love you versus how much you love me, right? So how many times do one node call the other node, right? And that's in counterterrorism or some of the things, this is important, not only knowing who was connected, but all of a sudden, someone gets 1,000 calls that all of the blue, and then an event happens or stuff like that, right? So it is important. Or again, how much information is transferred. So in this case, now you may see that here the network has non-direct straight edges. Why? Because if you have directionality and value, you want to know that this person is calling N5 more than N5 is calling N4, right? So the width or whatever tells you a little bit more. If it's not valued, if there's no value, with one just looking at the arrows, who sends, who doesn't, kind of thing, yeah? Now, what about the nodes? We've talked a little bit about the edges, how they come to be. Well, the nodes are important too, right? They have attributes. And more so when we're talking about social events or social studies, we cannot just ignore the nodes. So they can have their usual attributes we're used to, right? Categorical, numerical, etc., which you usually capture in the usual data way. You have your columns with your variables or attributes, and the rows are your nodes, right? But these can play a role in how you present your graph, and later on also on how you model them, right? So you could think of the size of the node is related to wealth, related. There's a study on the Italian families, on the Medicis, etc., right? So it tells you, well, sometimes just by looking at the size, you realize, oh, well, these were the rich ones. They're the big ones, and all connections are going. Maybe it's because of that. Or you could be looking at coloring for certain behavior. In a little study we did for schools, we had the goody two shoes, the really bad ones, and then okay, yeah, you don't want to do away with them, so you may color them that way. And depending on how the nodes and the edges change, it might tell you a story. Yeah? Okay. Now, the analysis, right? So this was just a representation, which already starts telling people sometimes a story. But then there were some studies that said, well, we need to look at something else. What else can we get from those networks, right? So the first things were the analysis of the structure of the network. You have a network, rather than thinking of how it was generated or whatever, what can I read from it? What is that structure, right? So some of the first studies were, as I say there, they were node position based, right? Because it's not the exact XY position, but position in the network, right? Relative to the others, where am I, right? So it's most frequently described by measures of centrality or prestige, right? And there are many, right? There's betweenness, there's too many, right? But the main thing is that all of them have some idea that is that some members are, due to their actual structural position, differently prominent, right? So they may become brokers, they may be popular, they may be isolates, there may be things that play a role, right? So the analysis, as I said, is through a relational lens, right? Is where are you with respect to the others, right? So some of the most and simplest used are talking about your in degree and out degree, which has to do with how many incoming ties do I have, how many outgoing ties do I have, right? So in this little example, everybody has an in degree of 1, except N1, who no one talks to, right? And N5, which has 9 incoming, right? So again, you start thinking about popularity or importance or certain things. And then out degree, well, in this case, all have 1, so everybody is sending 1, except the number 1 who's trying to talk to everybody. Please, no one sends me anything, but please let me call you. And N5 who says, I don't care. You're already talking to me. I don't need to send stuff. Yeah? Now, another measure that are important have to do with distance on paths from others, right? So one of them is betweenness. So on how many shortest paths does a node play a role? And this is important if you think that this is a train network. If N5 stops talking to N6, forget about, things happen, right? If this is the straight up form, okay, no, let's not go there, right? But things may happen, right? So betweenness, N5 and N6 have high betweenness. And some of these are very colloquial, if you can think they're really between the two groups, right? Take N5 and then you have two subgraphs. And then sometimes also another thing is closeness or reach, right? In how many steps can I reach someone else? Right, you might have heard people talk about the 6 degrees of Kevin Bacon or everybody separated, but supposedly based on real studies, if you distributed 12 ties from everyone in the world, we could all at some point reach each other, right? So in this case, everybody's close to everybody, right? Because it takes 1 or 2 steps to be able to connect with someone else, right? So again, these measures were based on distance and path from other nodes, the betweenness, the closeness, and there's many others that have to do based on the actual flow of information, whether they have control or not. And then they start taking also roles, right? Are you a broker or are you a bridge? Now there's other ways of measuring structure, right? Now based on actual network overall, those were thinking if you're a node, do you have high betweenness? Are you well connected? But you can actually also think of if I have 2 different networks, so what happens at the network level, right? So you can think of density, right? So if you think of the existing ties out of all the possible ones, right? So you go and say, I'm going to be super optimistic. We all talk to each other here. That would be, and choose 2, kind of thing of your connections. How many do I actually have? That ratio gives you a density, right? You can think of centralization. Now be careful, I talked about centrality, and that was about a node being central, right? But you can also have centralization in a network, right? If you have many people with many connections, then the network overall is not that centralized, right? But it tells you kind of how evenly spread the edges are on a network, right? So if you think of, again, this graph of star, right? This one, right, has high centrality, right? Everything is centralized between. In order to get information from N10 has to come to 5 to then go to, so there's a central place. So that's a highly centered. Not only is this guy have a high centrality, the network is centralized, right? And if you think of this other one, well, here there's no that, right? You don't necessarily need to go through M4, you go through N7 to go to N1. So it's not a very centralized network. So here's putting all of those kind of things together, right? So we can see here we have S and A are isolates, they're not connected to anyone, right? You can see M, B, and N, they're a clique in the sense that they're all connected to each other in every way. So the rest of the network could fall off, they would still be connected amongst themselves. You can see here the green one has high popularity, right? Everybody's sending stuff. Q here has high betweenness, right? Take Q out, and then these people are left alone. P is just trying to say, hey, please believe me, I'm here, I exist. And then, I mean, there's many reciprocals, but you can think of these are reciprocating their ties, right? So when you have something like that, it starts giving you a little bit of idea of structure. And there's a lot of different things that I'm not touching on. There's the theory of structural holes. So if you take this out, then you have a hole in the net. There's a lot of things, core, periphery, things that tell you things that could be related to a social aspect, right? Am I doing for time? Okay. Now, what if we just want to think of, okay, how I have these measurements? The typical question is, hey, after I did this intervention, is the density higher? Are there more connections, etc., right? So the thing with our usual statistics that we always have independent observations, right? And even when we think of, linear mixed models and random effects, well, those are repetitions of observations, right? It's not that your observation depends on another two observations behavior to get what you have, right? So then your analysis at the dyad or edge level starts getting a little tricky to if you want to use the usual things, right? So depending on the theory, on the social theory, mainly the creation of an edge depends on both, right? You can think of how expansive am I or how likable am I plays a role, right? So even if you really always talk to everybody, if this person is really hateful, you're going to be like, no, you're the one I'm not talking to, right? So it has to do a lot with both of them. So if you want to compare densities, which are pretty much, proportion, right? Proportion of ties, given the potential total between two networks, it is breaking away from just doing your usual test of proportions or confidence interval for proportions, right? Because the usual machinery is not going to work. But some of the advances in computing allowed the fact that you can actually just do combinatorial bootstrap, right? Now, it is still a little tricky, and you can read the Schneider's first paper, because, well, when you do bootstrap, it's really easy to just get rows, right? But here, you need to bootstrap nodes. And okay, if the nodes existed before, if they are different from what they existed, I can look at where their dyad was. But if they're exactly someone who existed, am I going to repeat it twice? So it's kind of a double bootstrap on nodes and on edges to then get an idea of what would be the distribution of the densities, and then say, okay, the one I have is this one, right? So then you get your confidence intervals and your standard errors through this process, right? That's as far as I'm gonna go. I'm happy to answer some questions, but I don't want to bore you even more. I know it's already been. So now newer, right, statistical theories and tools have gone through. You can actually do more hypothesis testing, right? There's a lot on random graphs and thinking, well, does this behave like a random graph? You can set a model, a generative model of what your network should be, and you can test if it behaves like that or not with some hypothesis. There's some regression-like models that let you assess influence of different variables, right? And when I say different variables, it's really many different variables, right? This allows you to try and test theories of a structure influencing behaviors or behaviors influence structure, right? It's been used in smoke cessation programs, same in schools, right? Okay, if I switch the seating around, will the quieter people get the really rowdy people to be quiet? Many things, right, that you can try and test. And there's also allows you to look at longitudinal theories of contagion or selection, right? Again, do I self-select myself to be part of a group, or am I, infected by the whole idea or the theories of a friend is my friend, or birds of a feather flock together, right? So we're starting also to talk about transitivity. If I talk to Gordana and Gordana talks to Luz, will Luz talk to me, stuff like that, right? Now, these models take a network set of edges, right? It's that adjacency matrix as the response. So think of, your usual Y in a regression setting. But then now your explanatory variables, and these are the exponential random graph models, which are the newer-ish ones, right? You can not only have node attributes, but edge inventory, right? And when I say the inventory of edge, like what do you see in the network? Do you see many open triangles? So, again, the example, there's a connection from me to Gordana to Luz, but there's none there. So is that happening a lot? Does that help me see how the network behaves or not, right? So think a little bit analog or a twist of your usual logistic Poisson regression models, right? Because you are at the end going to be looking at the probability of a dyad happening. But again, the unit is your dyad, and the dependency is on the rest of the network, right? Not only on one thing. And the estimation is going to be very different, right? It's going to be mainly a Markov chain and other things. So the model is looking at the probability of an edge between two nodes existing, conditional on the rest of the network, right? So both on how many ties I've observed, how many nodes I have, how many ties could exist, right? And also on the node attributes. So, are sporty types more likely to make friends than non-sporty in middle school, right? So you could use the actor's sportiness if you have a level of sportiness as a node level attribute. The dyad connections, right, are connections more likely within the same department, right? So that is look like it's a node attribute, but it really is, am I connected in the department? So you can use that too, right? So the edge inventory, again, there's many, many, many options, right? Think of, if you think of 3 nodes in a directional networks, there's about 64 potential networks, right? No one talks to no one, everyone talks to everybody. I talk to you, but you don't think of all, right? So you can say just, well, given the number of edges, given the number of reciprocal or mutual edges, right? If you care about just certain nodes of certain type, or you can think of triads, right? So I have 3. Is there transition? Is there no transition? So it is a more complex model, right? Now, what about time? All I've said right now is we have a network, right? So ERGNs, right, the exponential random graphs and the other analysis are applicable really to static networks, right? Why static? Well, I mean, you have cross-sectional data, which can be a snapshot of the moment, or it could be an accumulation, right? In the last year, this is how people have connected. But if you really think of it, most real social happenings evolve through time, right? You get to know me. People who met me today said, "Oh, nice to meet you," said, "Give it 10 minutes," right? So the potential of, oh, we're going to be friends may die very quickly. And then, so things change, right? So networks can grow or shrink over time. They can change network composition. People move away, people come in, right? Changes can just, the edges can change among the network members. So modeling network dynamics would really allow you to see that potential underlying social mechanisms of contagion or, homophily, trying to have people who look more the same to be together, right? Now, for that is the work of Schneider's, and actually our own Australian, like Pete Patterson has done a lot of work here, right? These are the stochastic actors based models for network dynamics that really tackles this, right? So now you can have networks evolving, and then you can try and see, okay, what influences. So this takes a little bit more, and I'm not going to go too deep into, unless you ask me, but it takes a little bit more of the point of view of what is generating my network. So is this generative process actually giving me the network I see? How does it apply, right? So some existing tools, UCINet is mainly basic structural analysis, good visualization. Pajek comes with it, and NetView too. Gephi, those are links, so you could click on them once I pass them out. Python, obviously, you can use ERGMs and visuals. R is really the one of choice. You can do structure, ERGMs, dynamic networks. There's many packages. The StatNet people have a nice StatNet web, right? So you don't necessarily even need to have R. You can just go and do some work in there, do some tests. And I'll just give you some overall examples, right? A social psychologist trying to study peer effects on attitudes. In public health, you want to model transmission of disease, right? Spread of health behaviors. In social workers, approaches to understand provision of social support. Actually, I had the bipartite tumor network. One student was doing work on dementia, access to dementia, and the study actually went with they have time. Yeah, they created a little vignette where it said, well, this is the usual, it's a silly word, but progression. I know it's not progression, but moving forward of the dementia. And they posted to program workers, to MDs, etc. What are the resources you would tell your patient that exists, right? So it was a bipartite network on how were certain groups connecting to other groups and seeing what was existing or not. And you could, there's been work done on network influence on physical activity in children. This is a very silly, simple example of some work we did a long time ago, just simple network level measures. These were the students in rooms. This is just an example of the don't get along network. So at time one, the density was 20.5, and at time two, it was 10. That's what you want to see, right? You want people to get along. And whether it was boiled down to is it significant, yes or no, the number of isolates or the percentage of reciprocal ties. Well, that one you can see that the percentage that just tells you that, well, still people who don't get along still don't get along with themselves. The colors had to do with goodies or not to goodies, and there was someone who actually became more of a baddie, etc. There's some works on affiliation. This person, Rhonda, did some work on infectious syphilis outbreaks in Calgary through the contact of social venues. So this was work on bipartite networks. And then there's things on more on models, right? Stochastic agent modeling for understanding dynamics of peer contagion, homophily and contagion again for weight similarity on given weight of people. And then some on methods. So when I was doing my postdoc with Hugh Chipman, I was doing some data mining methods for transactional graph data. So it was before Schneider's came out with some more of that other work, right? Because also when you have just transactional data that's coming to you, A talks to B, then B comes to C, etc. And then other work from Hoff, and here we have Schneider's and Pip, right? So the random P star model, so some of the exponential random models. And just a quick check, you can see how social network analysis has gotten way more publications in health. That's from PubMed, all from 79 on. That was just from U of W in the last 10 years, around 24,000. I didn't see that you could see this in there. Anyway, right? And so, ta-da! Questions, I'm happy to entertain them. I don't know if I'll be able to answer them, but I'll entertain them. Yep.
How do you think, from your perspective, of social network analysis? I just did a PhD on information questions, and I applied many tools from SNA to genetic networks. Many of the tools that you've mentioned, I've explored. I mainly ended up using a package called Multinet, which basically transforms your temporal networks into like multi-layer networks, and it relates the nodes between layers. But from your perspective, talking about social network analysis to be applied to something like genetics, because we have also similar, if you want to say, we believe that when a group of genes are involved in, let's say, a similar function, so we can decipher a role to a gene that we can't really tell what it does. So we do meter detection, etc. But from your perspective, being an expert in social network analysis, what are some of the, if I want to say, properties that you believe that are purely social networks that you can't be applied to biology or to?
So,
Could you repeat the question?
oh, sorry. Okay. Tell me if I
Just
just okay.
Yeah.
Okay. So the question was, and you can completely come and slap me if I, given the first part that was wrong in your question was expert. No, I'm no expert. I used to dabble on this, and I'm interested, but the rest of your question is really interesting. How does the genetics, right, the use of social networks, where can you really separate what is purely thing that you could say, no, you shouldn't apply to genetics, and thing that you could apply to genetics, because in genetics, you want to look at which genes are involved or acting up at a certain time in a certain activity. Yes? Okay, good. Well, so two things. First of all, your definition, the definition of ties is really important, and function, right? One of the things that, and I know more of what's happening in neurology than in genes, they create correlations of what things have been lighting up rather than what lights up after, like by fMRI, right? In genes, it may be easier to say, okay, who's upregulated and who's downregulated at the same time. And I don't know if your connections are just by being up or downregulated or mutation-wise, right? So that definition is really important to know how you're going to create your network if you really want to see how your network evolves towards a certain effect. I wouldn't really necessarily say there's anything wrong or how you separate that. It's how you're going to model, right? Are you wondering what really gives, because a lot of these that I've shown is really on how you get to see the structure of the network. There is some work, actually, even UCINet had at the very beginning, where you could say, given this structure, I have another outcome, right? So my outcome is disease, no disease, etc. That may be related to function. Right. So then at the end of the day, what you use there, and people have done this for physical activity, is they get from the network measurements, they create covariates for a quote unquote usual simple logistic regression or stuff like that. Right. So I guess it all depends on where you want to be looking at, because a lot of this is how the network is working. Right. Some of the things are how the nodes behave or makes the network work. So I don't think there's anything wrong. It's just very difficult to, again, very important to define what are your connections. And that idea of the multiplex, it's also important, right? Because the different relationships within the genes could be the one that go out. And the first thing I would say is I applaud the work, because most of the time people go like, this gene causes that, right? And you're thinking, have you thought of the axons, the things that we say don't really are doing anything? That whole composition recipe is what's going to give you potentially a phenotype. Yeah? Does that give you I said I would entertain and that I would answer it right. Yeah.
Some questions in the chat.
Okay, I can look at them here, or you tell me.
Yeah, I can just. So, how does dynamic structural equation? How about dynamic structural equation modeling?
So SME is structural equation modeling for networks. Well,
I raised that question. Can you hear me?
Oh, yes.
Yeah, I would just thank you so much for that excellent presentation and amusing one. I'm just questioning the answer whether that DSEM could be a good model to describe the networking between different factors. Because it's
So
longitudinal and it's cross-sectional, and you also do a lag study. So what factor influencing which factor before and after?
yes, so well, I'll be completely honest. In my earlier younger years, I did have them. I actually thought of SEM as the hocus pocus of statistics, uh, because the basis of just trying to get correlations to tell you everything.
Correct.
But given a little more, you know, thoughtful sense of it, I guess the big difference here is you are how much of a network are you really creating? One thing is the relationship that exists between variables and the residual, because that's
Yep.
the main thing. And again, I'm not an expert on SEM, but you're just looking at residual variability once you've accounted for processes, right? Whereas in real networks, you're dealing with all the variability and all the relationships at the same time without them actually being statistical correlations, right?
Mhm.
So that's where I think use of SEM or of OSNA techniques on SEM problems may break down.
Right.
And,
Right.
and again, that's where I think I'm no expert in SEM, so
Sure.
that's as close as I'm touching it before I burn.
Thank you. So Alberto,
Yes.
one more quick question,
Absolutely, go for it. Yeah.
just to understand. You mentioned about longitudinal and time series data. So if you have that time series information, and obviously the dynamics change over time, so you're expecting that network relationship changes from one variable to another variable, the direction or the strength changes. So when they at the end of analysis, when they give you a kind of network, would that network be the best representation across all the individual association over time, or it explains the model that answers most of the questions, or it was most of the time it was the pattern of that association? The question is that what would that network present? Do you know what I mean?
Yeah, so the stochastic actor-based dynamic network is not trying to give you what is the best network, but it is from the point of view of what generated this, so that you can actually still think of quote unquote prediction in saying, if the network has looked this way at these different steps, bringing up to here, what are the things that have made the network be what it is? So you could potentially say, well, if I move on time again, right, to give you a little bit more of the background, it is based on Markov process. It has a lot of uh, details and issues on, you could have edges happening at the same time. So as in any, just like you do in survival time and other things, how do you break the tie of who came first, who came later, to create the tie and move from one stage of the network to the next stage, etc. Right? So it's not that it's gonna give you a network, it's gonna give you a model of, again, and just like any model, if you forgot to put in the presence of clicks, and clicks are really important to give rise to other connections, obviously your model is going to be misspecified, right? So it is not that it yields a network, it's yielding what the process may have more scientifically been for the network behavior that you observe.
Sure. Thank you. And that is not specifically for SCM. I was just generally
Yeah,
speaking.
no, this is in general.
Yeah. Beautiful. Thank you so much.
Does that confuse you more?
No. Thank you.
Yes,
Has social network analysis been used in health policy analysis?
Yes, if you look at the work of Carla High, and if you look at the work that the RAND group has done in the States, they've used a lot of that to measure smoking cessation and other kind of interventions, and they've also used it as a planning tool to see, well, if I'm going to do implementation science on the ground, how is it? What's the potential of it actually having some optic. That's the ones that are I'm more knowledgeable or got wind of. Yes. No disappointment face from the answer.
No,
Okay.
very happy.
Anyone else?
Sorry, do you have any tools for social network analysis?
So
Is that
the Snyder's the RCNA. So the whole Siena idea is how it is implemented in RCNA, which is the one where it has the dynamic networks, right? That you have the times for the networks, how we look at each of the times. And that's really one of the that I know, and again, I'm no expert, I used to dabble in this. It's the one that's the most used. Pip, Patterson, and several have been building on that because it's already a solid thing, right? How to try to create and take into account the dynamics. Yeah.
I know nothing about social networks analysis.
And now you know even less.
Yeah,
Like, what?
less. Now, so I'm thinking about one of the networks where you were showing that had the different groups sort of highlighted.
Yeah.
So, obviously you can use social networks to sort of identify those groups if they're not already apparent, but, obviously groups occur naturally. And so you can identify groups and then sort of characterize them, but for naturally occurring groups, there are characteristics amongst them as a group that also would influence paths and stuff. And so how is that incorporated into?
Yes.
these?
So as I said, depending on the view you take, you could be thinking of is the structure leading to behavior,
Right,
or the
yeah.
behavior leading to structure,
Yeah,
right?
right.
And with the dynamical ones, and even with the ERGMs, when you're putting node attributes, right? We are same career, we like the same type of movies, etc. That sometimes helps you explain. Oh well, it seems right. There's a point where it's kind of difficult to really say, oh no, we need to ignore that it's because they are this that they talk to each other. Right. I mean, I know socially, and it is it's kind of silly, but at the same time, it's simple how as humans we do have that little bit of. I mean, I can tell you, being an immigrant when I got to, well, I'm an immigrant here, but in Canada, you could see how people in Mexico, if they had met those other people in Mexico, they wouldn't talk to them. But now that they were in Canada, they were like always friends, right? And that was the environment creating a structure that wasn't there, right? And the node attributes were still the same. And you see that, right? But modeling, and that's where you need to be thinking of.
Yeah.
Either the actor ones with time is the one that allows you a little bit more because you can actually see how people merge to other people, right? Or if people from the same group, right? It is a little more difficult to really see. So what was first,
Right. Yeah.
right? The characteristic, the homophily, or was I really brought in, right?
Mhm.
But it is attempting to look at that, right? Whether the structure yields the behavior or the behavior the structure.